Alright, so this video will go over Unit 6, Lesson 1, which is finding area bounded between two curves or two functions. And what we'll be doing is we'll be looking at problems like this one, where we have two functions that are drawn, and we are interested in finding the area between them on some interval from a to b. And, how would we do this? So we know how to find area under a function from a to b. That is simply, right, if we call this like f, the integral from a to b, right, the definite integral finds that area beneath the curve between the x-axis. Okay, so we can think about this now. If I took g of x, okay, I could find that area pretty easily using the integral. And then if I took, let's use a different color here, like purple. Okay, if I took f of x, right, that would be everything under f. Right, well, if I subtract this red stuff, then what it leaves me with is just the stuff that I want. Okay, so it's, the same idea from geometry of like, if you have a circle inside of a square and you want to find the area of just the stuff outside the circle, well, what do? You take the area of the square and the area of the circle and you subtract them, and that leaves you with, the excess stuff. All right, so now how do we express this idea with integrals? Well, okay, what did we say? We're going to take the area of the whole region, right? Everything under f. So the integral from a to b of f of x. And then we're going to take the area under g. So we'll do the same thing. And then subtract. Okay, and that gives the area that we're looking for. Now we can generalize this if we go through some arguments and we draw some pictures and we look at a bunch of functions. What we will find is that we're always just going to take the function that's on top minus the function that's on the bottom. And so we end up with this idea. Okay, if we want to find the area bounded between two functions, then we can simply take the integral of the top function minus whatever function is on the bottom. All right, so like in our last example, f would be on top and g would be on bottom. We wrote it as two separate integrals on the last slide, but just remember when you're adding or subtracting an integral, that's the same thing as just combining the two things. Right, we can make that one integral. So this is the big idea that we're going to use. All right, to solve something like this. So, this could be a typical UConn question they might give you. Find the area bounded by these two functions on the interval from x equals 1 to 2. Okay, well, so this is where drawing a picture could be helpful. Right, so, okay, 2x, well, I know that just looks like some line like that. X squared plus 3, okay, that's some parabola. Right, like that. And then I want to go from 1 to 2. Okay, so when we say the area bounded by these things, we mean like the region contained within. Right, so what does our rule tell us, right? Do top minus bottom. Okay, so we'll do from 1 to 2 of the top function, which in this case is the parabola, minus the bottom function with respect to x. And we can do that out. We can certainly integrate this thing. Nothing's stopping us. And you know how to do that, and you took a whole test on showing me how to do that. I'm okay with you at this point now using the technology to find these things. So just to remind you, and I'll show you here, we can go to our graphing calculator. We can go to y equals. We can type in, what was the function? So it's x squared plus 3 minus 2x. X squared minus 3, or plus 3 minus 2x rather. So you type that in and hit graph. Let's just zoom standard. And then just second trace, and then 7, right? Integrate. And then type in your bounds. So we wanted to go from 1 to 2. It gives us 2.3 repeating, which, I'm going to show you is actually the answer. So I'll go ahead and do it out. But okay, which is 7/3. All right, and if you actually did this out and plugged it in, you would get, let's see, 2 cubed. And, this is just a lot of work, and you can still do this work if you want to confirm. But I don't need you to do that anymore. Right, and this gives me, what, 8/3, and that's plus 6 minus 4, so that's plus 2. And then that's 1/3, and that's plus 3 minus 1. Yeah, and so you can see the plus 2s are going to cancel out, and that gives you 7/3. All right, what I'm trying to say is you don't need to do this part anymore. I'm perfectly fine with you just using the calculator to get the answer. Once you've set it up, please show me this, but then let technology do the rest. Okay? That would be sort of an easier example. Something a little bit harder would be something like this. Okay, so area bounded by these two functions. So again, drawing a picture is helpful, and you can use your graphing calculator to assist if you forgot what these things look like. But hopefully we know, this is a parabola shifted up 3 units and pointing down. And this is a line going through 1 with a negative slope. All right, and so, when we say the area bounded by these functions, okay, we mean, just get a different color, right? We mean like this area right here. So the stuff in between the two functions. Well, it's easy enough to see which one's on top, right? The parabola is on top, and the linear function is on the bottom. The problem is we don't know the bounds, right? What do we put for our definite integral? So we need to find those, right? Like where's this and where's this? Now, again, your calculator is perfectly capable of doing that, second trace intersect, and please do feel free to use that. However, it is good to know how to find it by hand, say on a non-calculator portion of a test, like you're going to be doing for UConn, say in a few weeks. All right, so just remember to find intersections, you simply set these things equal and solve. So let's see, this is a quadratic, so we'll get everything equal to 0 and factor, right, and that gives us our two answers. Why are there two answers? Well, there's 2 points of intersection, and so that makes sense. And so those become our bounds. And again, we're doing the top minus the bottom. All right, use your calculator. And if you want to confirm, you'll end up getting 9/2 or 4.5. Right, you may want to try an example yourself. Okay, this example is very similar. If you want to pause the video and try it, and I'll catch up with you. Right, so again, drawing a picture is helpful. 2x, again, we know looks like that. X squared minus 8 is some parabola shifted down 8 units. All right, so now we want to find the region bounded by these two things. Okay, again, it's easy to see. In this case, the line is on top, and the quadratic is on the bottom. But we need our bounds. So once again, either using the calculator, second trace intersect, or setting them equal. Solve the quadratic, get it equal to 0, factor, etc., etc. By this point, I think we're all okay with doing this. And so those are my bounds. And you always just go from left to right. If you were to go the other way, what would end up happening is you'd get a negative result, which can't make sense because we're talking about a geometric area. So if you get a negative result, usually that just means you set something up backwards, whether you switched these by mistake, that's common, or you by accident, you integrated from 4 to -2 instead of 2 to -4, or -2 to 4. Right, and just getting the answer. So I'm gonna, again, I'm not gonna do this out if I don't have to. I'm gonna let the technology do the heavy lifting. All right, the parentheses matter here because that, the negative's being distributed. Let me get the big viewing window up. There we go. All right, and again, we find our bounds, which we found were -2 and 4. And there we go. The answer is 36. Okay, and again, that represents the region, the area of that region. All right. One thing we just need to be careful of is sometimes a function can change, right? Which one is on the top and which one is on the bottom. So if this were f and this were g, right? If we were trying to find, let's just say they asked you to find this entire region, you would just need to be careful because, yeah, f is on top here, but then f is on the bottom here. And, if you think about this for long enough, you realize, well, okay, couldn't I just split this into 2 problems? Couldn't I find this area and just add them together? Yeah, that works. All right, that's just one consideration that you need to take into account. Which one is on top might change over the course of your interval. All right, one final thing, and this is a little tricky, is sometimes it is easier to integrate with respect to the y-axis rather than the x-axis. And to do this, we're going to do a problem that we could actually do either way. And then I'll show you a problem that's easier to do by going dy rather than dx. But let's say we were trying to find the area that I just shaded. So, using what we just saw, we could do top minus bottom. And let's actually do that so we can get the answer. So the top function in this case would be y equals 4. Just a vertical line or a horizontal line. And then the bottom function, of course, is x squared. And we would integrate that from 0 to 2. So let's do that out real quick. 4x minus x cubed over 3, and from 0 to 2. And let's see, if I plug in 0, that all just goes away. So I really just need to plug in 2. So that's 8 minus 8 thirds. And so let's see, that's really 24 thirds. So this is 16 thirds. Okay, so I thought of this as being my top function, this as being my bottom function. All right, but now a different way to think about this. And this is teaching you a new technique. We are used to drawing rectangles this way, with a function value as our height, and then some change in x as our width. Okay, that's where the dx comes from when you're doing this. What you're really doing is you're adding up a bunch of rectangles, an infinite number of rectangles, right? And dx represents that width, and f of x represents that height. So now let's just consider, instead of going that way, what if we were to go this way? Right, and use rectangles going up and down, some delta y instead. Okay, so now let's see. This would be some change in y. This, okay, I could think of as using the inverse function. So you learn in pre-calculus, right? If this is x plus 2, then f inverse is x minus 2, right? It undoes f. We can think about switching this thing around. right? X is going to be the square root of y, really plus or minus square root, but we're not concerned about the negative branch, so we're just going to concern ourselves with the positive. Right, I can think of, instead of integrating as a function of x, I can think of this thing instead as a function of y, or an equation of y. And so I can set this up like so, integrating now in this direction, okay, integrating this way. Because normally, again, we go from negative to positive right on the axis. So we're still going to do same direction, negative to positive, 0, in this case now to 4. Okay, because again, we wanted this whole region. All right, well, let's do that out. Let's see if we get the same thing, right? It should be this answer. So, okay, square root of y, that becomes 2/3 y to the 3/2. We do the fundamental theorem. If I plug in 0, that just goes away. So I just need to do 4. And 4 to the 3/2 is 8. And sure enough, it's the same thing. Okay, so we can integrate vertically rather than horizontally. Now, why on earth would we want to do that? Well, here's an example. Okay, something like this. Let's say we were trying to find the region bounded by these two things. If we were to do this with respect to x, and we could, it would be a little difficult because the top and bottom functions are going to change as we move across the region. Right? So like over here, this one's on top and this one's on bottom. But over here, if I try to find this slice, this is on top and this is on the bottom. Okay, well, so now I'd have to set up two integrals, right? I'd have to split this thing up, and I'd have to find this part, and I'd have to find this part and add them together, and I can certainly do that. And if you want a challenge, by the way, feel free to try to set that up yourself. But there's a much easier way to do this, which is don't go this way, but instead go this way. Right? Go vertically, draw vertical rectangles. Because if we do that, now all of a sudden, this is always going to be to the right of this. And instead of doing top minus bottom, okay, we can do right minus left. Okay, and so what we're going to do, we have to do this, though, we got to get it in terms of y. So I'm going to rearrange now. All right, if y equals x minus 2, then that means x equals y plus 2. And if y equals plus or minus the square root of x, that means x equals y squared. Okay, so I'm just solving for the other variable. And now I'm going to integrate. Okay, right, so what function is on the right? Well, this one. Right, so y plus 2 minus y squared. And again, I just need my bounds. Now, from looking at this picture, I can see that it's 2. And from looking at this picture, I can see that it's -1. Okay, but you could solve for that or use your calculator or whatever you need to do. But again, we integrate in this direction, so now we need y values rather than x values. Okay, and calculating that out will give us this region. Okay, so and really I'm more concerned, can you set it up and get the answer? But so it takes a little bit of time to get used to, but basically if it's easier to integrate with rectangles going in this direction, then this is the process you're going to use. And knowing which to use just comes with practice. All right, speaking of practice, there's an assignment on Canvas you could try. Please feel free to email me if you have any questions. Otherwise, thanks for watching.